In the last part, we learned about greedy best first search. It expands nodes that seem closest to the goal based only on h of n, which is the heuristic. The problem here is that it can be incomplete and non-optimal. On the other hand, what we saw in uniform cost search under the uninformed search category, they only considers the cost so far, which is g of n. If you remember, we added the distances from Arad to CBU by Arad, and and all the intermediate nodes, we added them. Uniform cost search is complete and optimal, but can waste efforts because it ignores future distances, like distance from CBU to Bucharest. So please understand, greedy best first search considers only the heuristic h of n, like from CBU, what's the distance to Bucharest. And uniform cost search only considers the initial part, the actual distance from Arad, what's the distance to CBU. Both have problems. Now, A-star search combines the strengths of both and forgets about the problems. The key idea is that A-star evaluates each node with this formula, f of n equal to g of n plus h of n, where g of n part is kind of contributed by UCS and h of n part by the greedy best first search. G of n stands for the cost so far to reach up node n. We also call path cost. H of n is the estimated cost from n to the goal, which is the heuristic. A star, so the f of n, this actually combines the estimated total cost of cheapest solution through n. So that's the meaning, estimated total cost of the path or the cheapest path through n. So A star always expands the node with the smallest f of n. So what is the intuition? So if we consider the Arad to Bucharest, the Romania map, g of n is the distance you already have traveled, and h of n is the straight line distance still left. Straight line distance was the heuristic we considered in the greedy best first search as well. So now f of n is basically the total trip estimate, how much I have driven plus how much I think it's left. That the how much I think it's left is the h of n, and how much I have driven is the actual distance I have traveled, that is g of n. A star avoids the greediness of only picking the nearest city, while also not being blind like uniform cost search. So we need to talk about admissibility and consistency now. So what is admissibility? For A star to be both complete and optimal, the heuristic must satisfy admissibility and consistency. Admissibility is the definition is a heuristic is admissible if it never overestimates the true cost. Never overestimates the true cost. Okay. So example is straight line distance is admissible. Okay, because the actual road distance can never be shorter than a straight line. Straight line is always the shortest distance between a pair of points among all the paths you have. Admissible heuristics are optimistic. They may underestimate but never exaggerate. Admissible heuristics are optimistic, okay? They never exaggerate. Consistency or monotonicity is a stronger condition. It's more like a triangle inequality. So it says that for every node n and its successor n prime, that means a child of node n, h of n is upper bounded by cost of n to n prime plus h of n prime. How the consistency works, we say that if there is a start node S and on the path to the goal, let's say there is another node n, and after some time there is another node n prime, okay, and let's say this is the goal node G, and so you can reach G from n prime. You can also reach G from n. Okay, so this is the cost. This is basically cost of n to n prime, which is cost is A, and this is h of n prime. Okay, so the estimated cost h of n, and this is h of n prime. That means the estimated cost from n to g, n prime to g. So what we are telling, estimated cost from n to g will always be less than this thing. Let's call it just c. Okay, so this is, we are telling h of n is always upper bounded by c plus h of n prime. So this is called the triangle inequality. Basically this arm of a triangle is less than the addition of this and this. So this is triangle inequality, and it's like, it's basically says straight line distance is consistent because direct path is less than equal to indirect path. Okay, direct path is less than equal to indirect path, and every consistent heuristic is admissible, but not every admissible one is consistent. This is important. Okay, every consistent heuristic is admissible, but not every admissible one is consistent. So what are the properties of A star? What is the properties of A star? Completeness. Okay, tree search A star is complete if h of n is admissible. But graph search, if you remember graph search where we keep track of the visited nodes, graph search A star is complete if h of n is consistent. Okay, remember these things. Tree search is complete if A star is admissible, h n is admissible. Graph search is complete if h of n is consistent. Optimality, the first goal expanded is guaranteed to be optimal. If you have multiple paths to the goal or multiple goal nodes, the first goal you expand is guaranteed to be optimal. Efficiency, A star is optimally efficient. No other algorithm using the same heuristic can expand fewer nodes while reaching the goal. So there are some limitations also. Okay, so the time and space complexity is still exponential. In worst cases can be order of b to the power d, where b is the branching factor and d is the solution depth. It's memory hungry, keeps all generated nodes, often runs out of the space before time. There are some trade-offs. You can use variance for faster and but suboptimal solutions. Sometimes it allows heuristics that slightly overestimates non-admissible to save time. So that is about A star search, which is nothing but a combination of the good points or the beneficial or pros of uniform cost search and greedy best first search. This admissible plus consistent heuristics guarantees optimality. A star is extremely powerful and widely used, okay, for route planning, puzzles, robotics. The limitations are its exponential growth and high memory usage.